Look up on a clear day and the sky is blue. Not white, like sunlight actually is. Not violet, even though violet light bends and scatters even more than blue does. Somehow, out of every color in sunlight, the atmosphere paints the sky one very specific shade, and paints the sunset a completely different one. There's an exact reason, and it's hiding in a single physics law. This is symmetry. Let's find the exact rule that turns a beam of white sunlight into a blue sky and a red sunset. Start with what sunlight really is. It isn't one thing, it's a mixture, every wavelength stacked on top of every other, and each wavelength is a different color. Send a beam of ordinary sunlight through a glass prism and it doesn't come out white. It comes out as a continuous band, red, orange, yellow, green, blue, violet, in that order, blending into each other with no gaps. The prism didn't add anything. It only separated what was already there. Every one of those colors was present in the original white beam the whole time, riding along together as a single ray. White light is not a color at all, it's the sum of all the colors, and the prism is just the tool that pulls the sum back apart so you can see each piece on its own. Each of those colors is really just a number, a wavelength, measured in nanometers, a unit so small that about 2,000 of them fit across a single human hair. Violet light has the shortest wavelength the eye can see, around 400 nanometers. Red has the longest, around 700. Blue sits in between, around 470. Orange, yellow, and green fill the rest of the gap in order. So when you say blue light and red light, you are really describing two waves of different lengths. Blue's crests packed closer together, red's crests spread further apart. That single difference, wavelength, is about to explain the entire color of the sky. Draw those two waves side by side, and the difference is obvious. The blue wave's crests arrive close together, tightly packed. The red wave's crests are stretched out, more relaxed. Both waves carry the same kind of energy, both travel at the same speed, the speed of light. The only thing that separates them is this spacing, and spacing turns out to matter enormously because of what happens next. Both of these waves are about to hit something almost too small to imagine. A single molecule of air, and how each one responds depends entirely on how tightly its crests are packed. Now zoom in absurdly far, past the wave, down to a single molecule of nitrogen floating in the air. This is where scattering actually happens, and it happens because of something hiding inside every atom, electrons that can be pushed. A light wave isn't just color, it's an oscillating electric field, flipping direction back and forth as it travels, exactly as many times per second as its wavelength demands. When that field washes over an air molecule, it grabs the molecule's electron cloud and shakes it back and forth in exact rhythm with the wave. For a moment, the molecule isn't just sitting there, it's got a slightly negative side and a slightly positive side, flipping polarity in sync with the light. It has become, temporarily, a tiny oscillating antenna, driven entirely by the wave passing through it. Here's the part that matters. Any electric charge that oscillates broadcasts its own wave, in essentially every direction at once, the same way shaking one end of a rope sends ripples out along its whole length. So the instant that molecule starts vibrating, it becomes a tiny transmitter, radiating a fresh wave of light outward, up, down, sideways, backward, at the exact same wavelength that drove it. This re-radiation is what scattering actually is. It isn't light reflecting off a mirror. It's every single air molecule catching sunlight and rebroadcasting it in every direction, all at once, all across the sky. But not every wave shakes that electron equally hard. A wave with tightly packed crests, blue light, forces the electron to reverse direction far more often per second than a wave with spread out crests, like red light. And an oscillating charge doesn't radiate energy in proportion to how far it moves. It radiates in proportion to how sharply it accelerates back and forth. Shake something twice as fast, and you don't just double the broadcast, you get dramatically more. Because the acceleration itself scales up with frequency. Blue light's tighter crests are about to translate directly into a far louder broadcast than red light ever produces. Push this one step further, and the pattern completes itself. The power an oscillating charge radiates scales with the square of the charge's acceleration, And acceleration itself scales with the square of the driving frequency, since shaking something back and forth twice as fast requires 4 times the acceleration. Square that relationship once more to get radiated power, and the result scales with frequency to the 4th power. Frequency and wavelength describe the same wave from 2 directions inversely related to each other. So frequency to the 4th power becomes 1 over wavelength to the 4th power. That's not a coincidence noticed after the fact, it's the direct consequence of how an accelerating electric charge radiates, exactly as the equations of electromagnetism predict. Physicist Lord Rayleigh worked out exactly how much louder, and the relationship is almost violent. It doesn't grow gently with frequency, it grows with the 4th power. Here's the law itself. The intensity of light scattered by a molecule is proportional to 1 divided by the wavelength raised to the 4th power. Not the wavelength itself, the 4th power of it. That exponent is the whole story. A small difference in wavelength between 2 colors doesn't create a small difference in how much they scatter. Raising a ratio to the 4th power massively amplifies it. Halve the wavelength, and you don't scatter twice as much light, you scatter 16 times as much. This single exponent is why the sky has any color at all, instead of being a uniform, boring white. Plug in the real numbers. Red light's wavelength, 700 nanometers, divided by blue's, 470 nanometers, gives a ratio of about 1.5. Raise 1.5 to the 4th power, and you get roughly 4.9. Blue light scatters almost 5 times more strongly off every air molecule than red light does. Every molecule in the sky is bombarded by the whole spectrum of sunlight at once, but it throws blue photons off in every direction about 5 times more often than it throws red ones off. Multiply that by the entire depth of the atmosphere, and the effect stops being subtle. Line up every visible color by wavelength and stack their scattering strength as bars, and the pattern is stark. Violet, the shortest wavelength, scatters the most of all. Blue comes next, still very strong. Green, yellow, and orange scatter progressively less. Red, the longest wavelength, barely scatters at all, most of it just keeps going in a straight line. So if scattering strength alone decided the color of the sky, the tallest bar says the sky should look violet, not blue. And yet it doesn't. Something else is still missing from this picture. The missing piece isn't in the air at all. It's in the sunlight arriving in the first place, and in the eye doing the looking. Sunlight isn't an equal mix of every wavelength. Plot how much energy the sun actually puts out at each wavelength, and the curve peaks in the blue-green part of the spectrum and tapers off sharply toward violet. There simply isn't as much violet light in sunlight to begin with compared to blue. So even though violet would scatter even more strongly than blue if given equal amounts of each, the earlier bar chart showed exactly that. There is noticeably less violet available for the atmosphere to scatter in the first place. The starting supply already tilts the outcome away from violet. The second piece is U. The human eye senses color with 3 types of cone cells, tuned to roughly red, green, and blue-violet wavelengths. But that third cone type, the one responsible for sensing the short end of the spectrum, is tuned to peak around blue and blue-violet. Its response actually falls off again as wavelengths get shorter, deeper into true violet. So even the violet light that does scatter and reach your eye triggers a weaker signal than blue light does. Your own biology is quietly turned down at exactly the wavelengths where violet would otherwise win. Multiply all 3 curves together, how strongly each wavelength scatters, how much of it the sun actually sends, and how strongly your eye responds to it, and the combined peak doesn't land on violet anymore. It lands squarely on blue. Violet was only ever winning one of these 3 contests. Sunlight supplies less of it, and your eye is less sensitive to it. And once both of those are folded in, blue comes out on top by a wide margin. That's the full answer, not one cause, but 3 curves stacking on top of each other. The same exact law explains the opposite extreme. At sunset, sunlight has to travel through vastly more atmosphere before it ever reaches your eye. At noon, sunlight coming from directly overhead punches straight down through the atmosphere, taking the shortest possible path to your eye. At sunset, the sun sits near the horizon, and its light has to travel sideways through the atmosphere at a shallow angle, a path many times longer than the noon path, cutting through dramatically more air and dramatically more molecules before it arrives anywhere near you. Send a beam of white sunlight down that long sunset path, and every molecule it passes has another chance to scatter its blue component off in some other direction, away from your eye, exactly as the earlier law demands. Over such a long path, this happens again and again and again. By the time the beam has crossed enough atmosphere, essentially all of its blue and violet content has been scattered away into the sky, somewhere else entirely. What survives the trip, mostly undisturbed, is the light that barely scatters at all. The longer wavelengths, orange and red. So at sunset, you're looking at two different products of the exact same law. Straight overhead, you still see blue, scattered sunlight arriving at your eye from every direction, same as always. But look toward the sun itself, low on the horizon, and you're seeing the light that made it all the way through that long path without being scattered away. The reds and oranges left standing after everything else was stripped out along the way. This exact law doesn't only explain Earth's sky, change the size of the scattering particles, or change the atmosphere entirely, and the same physics predicts a completely different color overhead. Rayleigh's fourth power law only applies when the scattering particle is much smaller than the wavelength of light, which is exactly true for a single air molecule. But dust, water droplets, and pollution particles are often much larger, close to the size of the light wave itself, and particles that size scatter almost every wavelength with roughly equal strength instead of favoring blue. That's why a hazy or polluted sky looks pale, whitish, or gray instead of a rich blue. The air is full of larger particles, diluting the sharp blue bias, with scattering that doesn't discriminate by wavelength at all. Same underlying idea, oscillating charges re-radiating light, but a different size regime with a completely different rule. Push the idea to another planet and it gets stranger. Mars has an atmosphere too, but it's thin, and almost none of its color comes from scattering off gas molecules the way Earth's does. Instead, Mars's air is loaded with fine reddish dust, particles far larger than a single molecule, so Mars's daytime sky scatters light the way that dust behaves, not the way Rayleigh's law predicts, and the result is a butterscotch, rusty color instead of blue. Same starting question, why does a planet's sky look the way it does? But a different answer, because the sky's color was never really about the planet. It's about whatever is actually doing the scattering. So the sky is blue because air molecules scatter short wavelengths far more violently than long ones, a fourth power law discovered by Rayleigh. It lands on blue instead of violet only because sunlight supplies less violet to begin with, and your eye is tuned to respond less to it. That same law, run over a much longer path, is exactly why the sun turns red as it sets, and run with a different particle size entirely, is why a hazy sky turns white and Mars's sky turns butterscotch. One rule, 4 different skies. If you want more ideas like this explained from first principles, subscribe Symmetry. See you in the next one.